All right. Oh, because I'm just used to doing things. Just highlight cells and then Control C and Control V. Control C copies, Control V pastes. So just grab the B data. Just grab the B data there. Nope, you don't need the B, you just need the numbers. Yep, Control C, Control V. Yep. All right, go back, highlight the B. Control C, Control V. Yeah, there you go. You don't need to copy A because A is already there actually. So just do C and D now.
Okay.
Yep. And then get rid of all those rows below and get rid of any columns you don't need. Okay, so with the data in this form, you basically have each supermarket makes up a row and each brand makes up a column. So those are our two treatments. We have 4 brands. I think I said pasta. Actually, I don't know what it might be, but let's just say that it's pasta. 4 brands of pasta across 10 different supermarkets. And we want to know what the supermarket effect is. And since the supermarkets in this case is rows, rows would basically be supermarkets. And since the brands are in columns, the sums of squares columns is variation due to brand. And then because this is a non-replicated two-way ANOVA, there is no interaction term, so the only thing left is the residual, and then all of the residual terms should add up to the sum squares total. So whenever you're looking at variation among rows, whether it was in the RAT data set or whatever, we relied on row means. And so in order to calculate sums of squares rows, you have to have the row mean, and you have to subtract from that the grand mean, and then you're going to square that. So obviously the first thing you need is row means in order to calculate sum squares rows. So quickly calculate the row means. You can use the AutoSum function if you're in Excel, just to calculate the average. And then once you have that done for one row, you can do it for all of the other rows. And if you want to keep yourself straight, you can put a label up there that says row means. In a similar way, if you want to know what the sums of squares of columns is, sums of square columns is basically the column means minus the grand mean squared. And so we can also generate the column means. And go down to the base of the column. Once again, just use the average function, and then you can drag that across, and you can get the column means. But then, of course, you also need the grand mean. You can calculate the grand mean one of 3 ways. You can calculate the grand mean by basically taking the average of the rows. So we can go here and just get the average of the row means. We can also get it by taking the average of the column means. We can also get it by basically just taking it as the average of the entire data set. And those should all give us the same value. It doesn't really matter which way you do it. Now, In this case, you can do averaging of columns and averaging of rows because you always have the same number of observations in each row, and you have the same number of observations in each column. This is one of the things that will generally happen in an unreplicated two-way ANOVA design. So once you have that, you can basically make a column here where you're going to calculate sum squares due to rows. And this is just simply going to be equal to the row mean minus the grand mean squared. And once again, we can make this a static cell reference by putting $signs in front of the G and the 12 in my case. And when we copy this down, we have all of our sums of squares due to rows, and then we just sum those up. And so in this case, we would use the sum function. And I'm going to code this green just to keep myself straight. We can also do sum squares columns by basically taking the column mean minus the grand mean and squaring that. We can make this a static cell reference by putting $signs into it so that it's going to do it by the grand mean each time. And we can see that it is doing it by the grand mean each time. And then we can just sum that up. And this would then be the sum squares column. Okay? We can go back to the example that was worked out in the PowerPoint though, and one of the things that we will see is that when we look at our values for the sum squares, in this case sum squares brand is 0.05, and the sum of squares due to columns, sum squares due to brand is 0.05. And the sums of squares due to supermarket is 0.1745. And when we go to do our calculations that we just did, what did we find? Those are not the same. Why are they not the same? Because we just messed up the calculations we did because we didn't do what with our row means and column, our sums of squares rows and sums of squares columns. What do you have to always weight your sums of squares by? It is by sample size, and in this case, how many samples or how many observations are going into these row means for how many of these samples or how many observations are going into the column means? 10. So we have to not just sum them, we have to sum them and then multiply that sum times 4 in the case of sum squares rows, and we need to take that and multiply it times 10 for sum squares column, because that's how many observations are contributing to each one of these column means. In that case, we get 0.05. we get 0.05, and we get 0.14751, 1.7451. So that's the sums of squares rows, sums of squares columns.
Why did you multiply by those three?
So you multiply it times 4 because you have 1, 2, 3, 4 brands. You multiply the columns times 10 because you have 10 supermarkets. So always look to what's the number of observations that went into generating the row mean or the column mean. That's what you multiply it by. The column mean is a mean across rows, so how many rows are in your data set. The row mean is across columns, so how many columns are in your data set. Okay? All right, so we have all that. So we could start working on a rudimentary ANOVA table. In any ANOVA table, you have a source of variation, and in this case, we have a source that is the supermarkets. We have a source that is the brands, and then we have residual, and then we will have total. And so we can have the sums of squares for each of these. Sums of squares supermarkets is due to rows. So that is 0.1745. So I'm just going to do equals whatever that value is. And then sums of squares due to brands is equal to whatever that is. So now we can calculate residual a couple of ways, right? What are the couple of ways in which we can calculate residual? There's one complicated way and one easier way. Okay. So one way is to get the total. And so the residual would be sum squares total minus sum squares row minus sum squares column. So you might say, well, calculating sum squares total is a total pain in the ass, except that it's not really. What do we need to do if we're going to calculate sum squares total? What is sum square total? No. So a sum of squares is always a difference between something and some sort of mean. So sum of squares total is this individual value minus what? Minus the column mean, minus the grand mean, minus what mean? Minus the grand mean. So in this case, sum of squares total is pretty easy. It's just each of the individual values minus the grand mean squared and then summed across all values. So once we do this for one, we can do this for all. So if we take this first cell here, subtract from that the grand mean, we're going to make the grand mean once again a static cell operator, and then square that value. Once we have it for that one, we can then just drag down all 10 rows and drag across for the 4 columns. And then when we're done with that, all we have to do is sum that thing up. And when we sum that up, we get this value. So sum squares total should be 0.22936. Let's go back to our worked example and see if that is actually what we got. .22936. Put your blue sticky up when you've got that done. So you got it done correctly? Okay, cool. Go ahead and add that to your ANOVA table that you're developing. All right, everybody got it? Okay, blue stickies down. So now, if we want to know what the sum squares residual is, we can simply do simple subtraction. So we want to basically subtract from the sum squares total the sum squares supermarket and sum squares brands. And that should give us sum square residual, which should be 0.00485. And when we go back and look at our ANOVA table that was from PowerPoint the other day, we have that. So we could have also calculated sum squares residuals by doing a more complicated equation, which is to take the individual values subtract from that the row mean, subtract from that the column mean, and then add to that the grand mean. Square that, and then sum across all values. That's considerably more complicated to do, right? But you could, in theory, work through Excel and do that. It would be a pain because each cell would have to be done individually and you couldn't just copy formulae. But in theory, if you did this, it will give you the same answer by doing the subtraction way. If you want to demonstrate to yourself that that is true, you're welcome to plunk around in Excel and do that and demonstrate to yourself that that is actually the fact. So what else do we need in an ANOVA table? We need degrees of freedom. We have 10 supermarkets, so how many degrees of freedom do we have for supermarkets? 9. So we have 9 degrees of freedom for supermarkets. We have 4 brands, so how many degrees of freedom do we have for brands? We have 3. How many residual degrees of freedom do we have? If we go back to our formula here, the degrees of freedom is simply the degrees of freedom from one and the degrees of freedom from the other multiplied together. So this would then be equals 9 times 3, which you can do in Excel, or you can also just know that 9 times 3 is 27. Oh, except that I accidentally hit a minus sign somewhere in there. And then when you sum these things all up, they should be 1 less than the total sample size. The total sample size in this problem is 40, so these should add up to 39. So when we add them together, they should hopefully equal 39 if we've done all of our work correctly. Okay? Once again, the math should always add up. These always add to that. This can be derived not just by adding these together, but by looking at the total data set and subtracting 1 from it. Okay? Everybody with me so far? What's the next thing we need in an ANOVA table? We need mean squared. How do we calculate mean squared? Yep, it's the sums of squares divided by the degrees of freedom. And we do that for the supermarkets, the brands, and the residuals. And then we need F statistics for each of these things. What is F? It's the mean squared of whatever your treatment is divided by what other mean squared. Not the one right below it, but residual. Yep. So this is going to be, for supermarkets, it's going to be mean square supermarkets divided by mean square residual. And for brands, it's going to be equal to mean squared brands divided by mean squared residual. And then we would have to go and find what p-values are for this. And we would go to either R, where you can calculate p-values for F statistics, or you could just go to Daniel Soper's website and do it there. Either way, what it's going to do is it's going to give you the answer that we saw once again in PowerPoint. So going back to that, here is our result. And we have 92.78 and 107.944. So we got the answer that we expected. And in both cases, these are monstrously large p-values, or monstrously large F statistics, which means that they'll have really, really tiny p-values as a result of this. And the reason that you can only do residuals rather than the interaction is that this would also be the number of degrees of freedom for the interaction term. So if you go back to the PowerPoint from the other day. Oops, that's not the PowerPoint I wanted. Oh, I don't have it. Let me go back to this, and then let me go get another. I want to pull up the two-way ANOVA with replication so we can look at the ANOVA tables side by side. The interaction term for a two-way ANOVA is the number of rows minus 1 times the number of columns minus 1. That is the interaction term. Now, if you have replication, you have a bunch more data hanging around in your data set because you have replicates at each combination of row and column. Go back to the rat fat example. We have 2 columns. We have 2 rows, which means that we have 1 degree of freedom. We have 1 degree of freedom, which means for the interaction term, the row by column interaction term, we have 1 degree of freedom. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 observations total, which means that we have 11 total degrees of freedom, which means that we have 9 degrees of freedom left over. Sorry, not 9, 8 rather. 3 minus 11 is 8. We have 8 degrees of freedom for the residual term. And the reason that we have the main effect degrees of freedom plus the main effect degrees of freedom plus the row by column interaction degrees of freedom, and we have leftover degrees of freedom for residual, is because we have more than 1 observation in each of these spots. We have 12 degrees of freedom total. So that when we get to working out an ANOVA table, we have a bunch of degrees of freedom left over because we have replication, because we took more than 1 observation for each row-column combination. In an unreplicated design, we didn't do that. And so when we go and calculate the interaction term degrees of freedom the way we should calculate the interaction term degrees of freedom. In this situation that we're working with an unreplicated design, that basically uses up all of the remaining degrees of freedom. So if we made this the interaction term, that is the degrees of freedom for interaction. Row minus 1 times column minus 1. That then uses it all up because that plus that plus that equals the total degrees of freedom that you have. And so there's nothing left over for residual. So if you make the mistake of specifying a unreplicated two-way analysis of variance in R the incorrect way, you know, whatever your response variable is, whatever your rows are, whatever your columns are, whatever your data frame is, if you ask it for this and it's an unreplicated design, it's going to give you, under source, it will give you a row effect, will give you a column effect, and it will give you a row by column interaction, but that's it. If, on the other hand, you ask it for row plus column, it will give you row, column, and residual. And the residual line will be the same as the row by column interaction line. In this case, it will not calculate F for you because there is no residual value to divide by. There is no mean square residual because there's not a residual term in your model because you specified a model that has both a main effect, another main effect, and an interaction effect. If you use the plus sign, it's telling R, all you're looking for is a row effect and a column effect, and that's it. Okay? But in both of these cases, these two things will have the exact same sums of squares, and it will have the exact same degrees of freedom. What will change is that one will calculate F statistics for you, and the other will not. Because you don't have any degrees of freedom to test an interaction effect. There is no residual, because in this situation, what you would normally have is you would have another row here, which is residual, so that when you have degrees of freedom and sums of squares, you can calculate a mean square row, a mean square column, a mean square for the interaction, and a mean square residual. But because you used up all of your degrees of freedom on the interaction, there's no degrees of freedom for a residual term. And so you can never calculate a mean square residual. And because F is mean squared row divided by mean square residual, this doesn't occur. So as a result, you can't get an F, you can't get a P. Okay, does that make sense? And that's fine, because sometimes it's impossible to have replication. This would be one of those cases. You have store brands, you have brands in stores. You can't have multiple observations of the same brand in a store because all of the store brand pasta is the same price. The prices don't vary from box to box. At least they shouldn't, unless the pricing person has made a big mistake. Okay? Does that make more sense? Good. All right, go to R. I would save that thing that you just worked on under a different a different file name. and then close that file. And hopefully your regular price.dat file is still in its original form. And so hopefully your price.dat data are still in its original form because you saved what you were just working on under a different file name. If it's not, you have to go and put it all back the way it used to be, which is going to be a pain. But then save that under a different file name. Save that under. Okay, what happened there? The joys of technology. Did it actually sound like something shorted out when that happened? Ah, we're back. Okay, so pull up R and pull up whatever script you were working on last time that you were here, which for me is this thing, and then run it down to wherever you had it run down to before. So I had gotten this far down, I had made a plot. And once again, the nice thing about this plot is it tells you some things. So we saw, as a result of the ANOVA table, so we can go, just to make sure that we've calculated the ANOVA table correctly, we can go and rerun our analysis. And we can see that we got the same numbers as we got before. .17451, 0.05, 0.00485. We got the same F values, and once again, the P values are really low. That's telling you that the brands do differ from one another. Some brands are cheaper than others. It also tells you that the stores differ from one another. Now we can see that in this type of plot. This is the plot that we generated at the end of class last time. And you can see that brand B and C are consistently more expensive than brand A and D. You can also see that some stores, store G is a more expensive store, and stores J, E, and C are the three cheapest stores for the most part. And so there is variation among stores. But what you don't see around any of these data are you don't see any sort of variation. And so the other reason that you can't calculate an interaction term is you can't actually generate variation within sample variation for each combination of store and brand, because there's only one observation there. So we would normally, if we were going to graph something, we would graph means with their 95% confidence intervals. We would graph other means with their 95% confidence intervals. And then intuitively, when you create a graph for someone's viewing, you can intuitively say, does this mean fall within this means confidence interval? Does this mean fall within this means confidence interval? If they do, you would conclude that they're not different. And if they fall outside of those ranges, you would conclude that they are different. But we can't do that here because there's no within sample variation. Within a combination of supermarket and brand, there's only one observation. So, but we know that there is a effective brand, and we know that there is an effect of supermarket. So what is a meaningful graphic that we could make? And that's what I asked you to think about and work on between last time and now. So what did you guys come up with? How would you approach this? We know that there's differences among supermarkets because the ANOVA table told us that. How can we illustrate to a reader what those differences among supermarkets is like? We started down this path last time. Whenever you want to make one of these summary plots, what do you start with? What do you usually invoke in R? Not an analysis, we already did the analysis. So yeah, so we want to get summary data. And so what we did last time, let's just do CI plot 1. What we did last time was we invoked summary SE. And summary SE needs a couple of things. It needs a data frame, which in my case is dat. What else do we need? We need a measure bar, which in this case is price. And if I recall correctly, we have to put all these things in quotes. And then we need group vars equals. And then in this case, we concatenated and we asked it to give us supermarket and brand. And when we did this, it did something. What's that? Yeah, it gives you the NAs. So when we call this up, I was doing extra work after I left you guys last time. It's because it's CI plot 1. It gives you all these NAs. And so what R is basically saying is you asked me to divide up your data by supermarket and brand and calculate the mean, which you can't do because it's just the sum of the one thing divided by 1. But then you also asked me to give you the standard deviation and the standard error and the confidence interval. And I can't do those things because there is no variation when you divide up the data by both brand and supermarket. So I can't do that, so I'm giving you a bunch of NAs. It's basically R saying, screw you. You're asking me to do something I can't do. And that's because all it's done for you is it's just reproduced the data set. And so if you plot this, so I made a plot up here, and I was plotting the raw data, but I could also plot CI plot 1 data up here. It will basically produce this plot that I just had. But the first time I did it, I just plotted the raw data. So I can go back up here. I can change this to plot the data for me. So just plot the entire data set, and I get the same result. So that's really all it's telling us. Now, this plot is useful. What is this plot useful for? We can't test the interaction formally, but when we look at this plot, do you think that there's an interaction between brand and supermarket or not? why. If we look at brand A and D, the red and the purple, what almost always happens with red and purple? They're pretty similar, and red is almost always higher than purple. Red higher than purple, same. Red over purple, 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 red over purple. Only two with purple over red, and in those cases they're very close to one another. Whatever happens to red also happens to purple across supermarkets. Blue and green, right on top of one another. Blue over green, green over blue, green over blue, blue over green, green over blue, blue over green, green over blue, green over blue, blue over green. But in all cases, these things are very close to one another. Whatever happens to blue happens to green as you go across supermarkets. That is the very definition of a lack of interaction. When the response of one set of treatments is not affected by the response to the other set of treatments, you have no interaction. You only have an interaction when a particular treatment responds differently to the other treatment. And so in that case, these lines would not be paralleling one another. They would be crossing one another more often than they do. And they would be doing big crosses, not these little piddly crosses. And so even though we can't test the interaction formally, we can look at an interaction plot. In the business, these are called interaction plots. And we can say, well, even though there's an effect of supermarket and there's an effect of brand, we don't see in the interaction plot a lot of interaction, even though we can't test that formally with an F-test, because we just don't have the number of degrees of freedom. Now, we have these differences among brands that we found from our analysis. And we have these differences among supermarkets. How can we display these in a graphic that would make sense to people?
I don't know if it's correct, but what I did was, instead of the group lines and cat name, I just did
Okay, let's follow that advice. Actually, I should have, let me do it this way. I'm going to just copy all this. Change this to CI plot 2. And then just get rid of supermarket from this whole equation. Now I have a mismatch parentheses. When I do that, when I get CI plot 2, look at that. It has given me an actual mean for the 4 brands. It's given me standard deviations, standard errors, and confidence intervals. Because, let's go back. The replication for brand is provided by store. For brand, for brand A, we have 10 observations. The 10 observations are the 10 stores. For brand B, we have 10 observations. The replication for brand is the 10 stores. In the same way, the replication for store A is the 4 brands. Replication for store B is the 4 brands that are found within that store. In the same way that brand A is found within 10 different stores, brand B is found within 10 different stores. So now we have within sample variation to work with. Once we have that, we can go back. We could just copy our plot code from before. and plunk it down here. Change the data frame to CI plot 2 in my case. In this case, X is not going to be supermarket. What is X going to be? X is going to be brand. And there is no grouping variable because we're only plotting one treatment. We're plotting brand. So we would get rid of the rest of that. And should have named that plot 2. But unfortunately, when we did that, it gave us this. So what else do we need to add here? We need to add error bars. So we do that with geom error bar. We can just do open quotes, or open parentheses, but if we do open parentheses, we have to go up here to the aesthetics thing, and what do we have to add? Ymin, and so Ymin is equal to price minus CI, and we have to add Ymax, which is equal to the price plus this confidence interval. And now it should give us means with really shitty looking confidence intervals, but we know how to fix those things and pretty this thing up. And now this is useful. It's telling us brand B and C are more expensive than brand A and D. Well, guess what? We already suspected that because there's a brand effect, and when we looked at the interaction chart, brand B and C are always more expensive than brand A and D. But in this case, what it has done for us is we can now say that as you move from one brand to the next, there's actually a lot of variation around the mean for the brands. Well, that variation around the mean for the brands is that high because the stores themselves vary quite a lot in the prices that they're charging. So it should make sense to us that there would be quite a lot of variation. But there's not so much variation around the means that we can't still detect differences between the means or among the means, and that B and C are more expensive than A and D. If we wanted to do this for supermarkets, what do? Well, just take the code that you've already written, generate another set of confidence interval data, copy this, paste it down here. This will now be CI plot 3. And in this case, the measured variable is price, and the group variable is not brand, but actually what? Supermarket. What else do we need to change about this thing? Nothing, except that we need to make this now CI plot 3, and plot 3, and change the data frame that we're going to use to CI plot 3. Oh, X variable is, thank you very much. X variable is no longer brand. It is now supermarket. It would have given me an error, and I would have caught that in a minute, but you caught it before I did. Good. Helps if one knows how to spell. Now we have 10 supermarkets. Each of these has a sample size of 4 because we have 4 brands within each supermarket. And when we get this plot tells us that supermarkets vary. And it looks like supermarkets G and I are really expensive places to buy. Pasta and supermarkets C, E, and J are really cheap places to buy pasta. Once again, this conforms to our expectation if we go back and look at the interaction plot as well, because G and I are consistently higher than the rest, and C, E, and J are consistently lower than the rest. But once again, we can't know which of those is different from which, because there were no confidence intervals associated with those. So now we can look at these things and we can say, oh, well, A and B are definitely different. B and C are definitely different. A and C are not really definitely different from one another. Now, when we did a one-way analysis of variance, we could formally test these comparisons, couldn't we? How did we do that? And we actually did this did we do post-hoc comparisons in a two-way ANOVA that is replicated? We didn't. We need to go back and do that. Let's do that on Monday. Remind me, because we're almost out of time. So how do we do post-hoc comparisons? We would use a Tukey's on a significant difference test, and we would do Tukey on the model, whatever the model is. But in this case, it won't do a Tukey's test on the model that we tested because it has both features in there, and there's no variation in the interaction to test all possible combinations. So all we could do is we would have to modify the model so that the model only included supermarket or only included brand. But if we had a replicated ANOVA, we would be able to test both of those. So on Monday, homework for Monday, ungraded as always. Go back to the rat fat data. Run the analysis. And then figure out how to run a Tukey's on a significant difference test on it. Then deal with the supermarket data. Run Tukey's on supermarkets and on brands. And come to class ready to share what you did with others and see how you fare. Why am I giving you tasks that I haven't necessarily prepared you for specifically? So you can figure things out on your own. Guess what? You're going to have to do a lot of that after you leave here. I've been working on something. I agreed to give a presentation at a meeting some months ago, and that meeting is coming up here at the end of April. And it has to do with roadkill. I'm a herpetologist, and so what I've been doing since COVID is I've been running a particular line of road Well, that's not what I wanted to do. I've been driving a stretch of highway, basically from it's on New 210 from River Bend, basically out to Richmond. And I just stop and record every dead animal on the road. Ooh, so exciting. But the reason I started doing this was because during COVID, when COVID kicked up last year, one of the things I noticed as I was bicycling around town is that there was a lot less traffic. It was a lot more enjoyable to ride my bike for exercise because I wasn't having to deal with as many cars. There are fewer cars on the road, there are fewer animals being hit by cars, et cetera, et cetera. And so I started looking at roadkill. And so this is generated in R. There's a set of geographic packages in R that you can use to basically plot geographic data, latitude, longitude, things like this. But These kinds of spatial data sets are not particularly well developed in terms of R's ability to handle them and analyze them. Because one of the things that you'll notice is that in these areas where there's a lot of forest, you tend to get a lot of birds. In areas where there are less forest, you tend to get fewer birds. This is true for birds. It's especially true for mammals. Look at all these mammal sightings in this forested area from Orrick to Richmond. Relatively few mammals in here, and then lots of mammals once again in this forested area. Guess what? There isn't in R. There isn't a way to analyze linear features like this and say, are things located randomly along that linear feature, or are they clustered? So guess what I've been doing lately? I've been figuring out how to analyze these kinds of data because it's a question that I have about a data set, and there isn't really a good way developed right now to do it. If you go off and become a data scientist, which is what I presume you want to do when you're done, you're going to be faced on probably a regular basis with things nobody has ever done before. The whole reason that you're employed at a place that needs data scientists is because they're going to ask you to do stuff that's never been done before. Get used to it. I'm 54 years old, and I'm learning new shit that I've never done before. And quite frankly, not very many people have tried to do it before in the past either. I have a big long code. I have a big long script right now. It's 250, 300 lines long, and it's like, try this. Then some code of what I'm trying. Didn't really do what I was expecting it to do. Didn't work. There's a comment line that says, didn't work. Try this new thing. Some code, me trying something out. Didn't work. It's a lot of trial and error when you're developing something new. So get in the habit of being asked to do things that you're not necessarily prepared for, although you're somewhat prepared for, and figuring things out, because you're going to find that you have to do this on a regular basis after you leave here. So